The island of Madeira drops straight into the Atlantic. There is almost no flat land. The cliffs run directly to the water, and the valleys are too narrow and too steep for a standard runway. Yet more than 9 million passengers land here every year. The question this episode answers is a mechanical one. How do you extend a runway over the open ocean when the seafloor below you is too deep and too unstable to build on, and the cliff behind you cannot be cut back any further? The answer is a platform. Not a platform resting on the seabed, but one standing on 180 individual concrete columns rising from the water's surface. Before we get to why that works, we need to understand exactly why everything else failed. Madeira is a volcanic island in the North Atlantic, part of a Portuguese archipelago sitting about 1,000 kilometers southwest of Lisbon. Its terrain is essentially a mountainous ridge surrounded by ocean. The original airport, known for decades as Funchal Airport and later as Santa Catarina Airport, was carved out of a narrow coastal shelf on the island's southeastern edge, near the civil parish of Santa Cruz. From the very beginning, the runway was short. Not short by the casual standards of a regional strip, but short in a way that determined what aircraft could land, how fully loaded they could be, and how pilots had to approach. The terrain at both ends of the runway was unforgiving. One end faced a cliff face, the other end terminated at the coastline, with the Atlantic beginning immediately beyond the threshold. Madeira's importance as a leisure destination for European travelers kept growing, but the aircraft serving those routes kept getting larger and heavier. The runway could not accommodate them safely at full capacity. The airport had become a constraint on the island's economy, and the constraint was geological. You cannot argue with a cliff. The first serious attempts to solve the problem focused on what seemed obvious: reclaim land from the sea at the runway's ocean end. Build a seawall, fill it with rock, extend the pavement. It was the same approach used at dozens of coastal airports around the world. Madeira's seabed refused to cooperate. The ocean floor drops away sharply from the island's edge. At the depths required for a meaningful extension, a conventional fill operation would need an extraordinary volume of material that did not exist nearby in sufficient quantity. And the engineering loads on that fill, once saturated and subject to Atlantic swells, raised serious concerns about long-term stability. A filled extension of the scale needed would also have taken years longer and carried substantial risk of settlement, meaning the pavement surface could shift and crack after construction. Engineers were being asked to solve a geometry problem: extend the usable runway length by enough to change the airport's operating category, do it at the ocean end, and do it on a coastline where the seafloor offered no easy foundation. The solution that emerged was a platform elevated above the water, a viaduct structure in engineering terms, supported not by fill, but by a forest of reinforced concrete columns driven into the upper seafloor close to the shoreline, where the water and the substrate were manageable. The platform extension that was ultimately built measures roughly 1,000 meters in length and about 180 meters in width. It stands on 180 columns. That number is not decorative. Each column is a structural response to the specific load case it carries. The platform must support not just the static weight of the pavement and aircraft, but the dynamic loads from landing impact, rolling gear, fuel trucks, and the constant lateral pressure of Atlantic wind. Concrete columns in a marine environment also face corrosion from salt water and salt air, which means the reinforcement inside each column had to be specified for long-term durability, not just immediate strength. Beneath the platform's deck, the space between the columns is open to the sea. Waves pass through. This is intentional. A solid wall facing the Atlantic would absorb enormous wave energy during storms, transmitting those forces directly into the structure. The open column design allows water to move largely unimpeded beneath the deck, reducing the lateral load on the system as a whole. The engineering term for this is wave transparency. The structure is designed to let the ocean pass through rather than fight it. Construction on a structure of this kind in an open ocean environment creates problems that do not exist on land. Workers and equipment had to operate over moving water. Concrete pours had to be timed around sea conditions. The columns themselves had to be formed and cured in a saltwater environment, which affects the chemistry of the concrete and demands tighter quality control than an inland project. The overall airport reconstruction and extension project, which included not only the platform but also a new terminal building and associated infrastructure, was a major undertaking for a Portuguese island with limited land resources. The airport sits 13.2 kilometers east-northeast of Funchal, the regional capital, and by the time the expanded facility opened, it had become one of the more technically complex airport expansions in European aviation history. There is a consequence that tends to go unmentioned in the engineering literature, but that every pilot who has landed at Madeira will confirm. The runway's approach path over the water is unusual. Because the platform extends into the Atlantic, and because the terrain behind the airport rises sharply, the visual environment during approach is not the standard horizontal reference that pilots are trained on. The water is directly below the approach path, with no visual ground reference close to the threshold. Crosswinds off the Atlantic are frequent and can be strong, and the surrounding topography creates turbulence that is difficult to predict. Madeira has historically been rated among the more technically demanding approach and landing environments in Europe, and the expansion, while it resolved the length problem, did not fully neutralize the difficulty of the approach itself. The airport received a category upgrade after the extension was complete, allowing heavier aircraft on longer routes to operate with normal fuel loads. That was the core promise of the entire project, and on that measure, the structure delivered. The airport today is officially named Cristiano Ronaldo International Airport, renamed in 2017 to honor the Madeiran-born footballer. That renaming ceremony drew international attention for reasons unrelated to engineering. A bust of Ronaldo unveiled at the event became one of the more widely shared images on the internet that year and has since been replaced. The airport continues to serve as the fourth busiest airport in Portugal, and in both January 2025 and January 2026, it surpassed Faro in passenger throughput, a signal of how central the island has become to European leisure travel. The platform extension, now decades old, remains structurally in service. Its 180 columns continue to carry the weight of every aircraft that lands from the ocean end. The lesson Madeira teaches is specific and transferable. When natural terrain makes a standard solution structurally impossible, the engineering response is not always to find more material or more force. Sometimes it is to design for transparency, to let the environment pass through the structure rather than requiring the structure to resist everything the environment can apply. The columns work because they do not try to hold back the Atlantic. They simply stand in it. That distinction between resistance and accommodation is the decision that made the runway possible, and it is the same reasoning that drives platform solutions at coastal airports, bridges over tidal estuaries, and offshore infrastructure around the world. Madeira needed a longer runway. The ocean needed to keep moving. The 180 columns were the answer that satisfied both. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.